Today's topic is the fundamental theorem of calculus, and anything with a name like that, you know it's got to be important. This is really the key to this second half of calculus, where our problem is to figure out how much area exists under a graph above the x-axis under a function from point A to point B. That's been our goal. We've estimated it with different forms of rectangles and trapezoids. We have found them if they were geometric shapes. We've learned this thing called the antiderivative. Now it's time to put all that together and be able to find the area under any function from any start to any finish. Here's the solution. This is the fundamental theorem. The integral from A to B of a function is just f of b minus f of a. That's capital F of b minus capital F of a, where f, big F, is the antiderivative of little f. So what this means is to find the area, you just need to take the antiderivative, evaluate it at the top and bottom integration limits, and subtract. All right, so let's see that in an example. We're trying to find the area here under the graph of x squared plus 1 from 1 to 2. And so we've got a few steps and we find that area. I want to encourage you to kind of keep in mind what a reasonable answer would be. Each of these squares is one square unit. I've got 1, 2, 3 would, this box isn't quite full, but if I take some of that area and put it here, I'm thinking my answer should be somewhere between 3 and 4. That's just an estimate to have an idea when I'm done if it's a reasonable answer. Now my steps are, take the antiderivative. Antiderivative of x squared is x cubed over 3. The antiderivative of 1 is x. Usually the way we arrange this is we put a big vertical line and we put the limits of integration over here. Once you've taken the antiderivative, the integral symbol's gone, but I still need the 1 and the 2. And technically that's x equals 1 and x equals 2. So now what I need to do is plug in the 2, plug in the 1, and subtract the two results. So I like two big sets of parentheses, one for the number I get when I plug in 2. All right, so let's plug in 2. 2 cubed over 3 is 8/3 plus 2. All right, that is literally taking the 2 and putting it wherever I see an x. All right, 8/3 plus 2. When I plug in the 1, I get 1/3 plus 1. And the fundamental theorem says there's a subtraction sign in between those two, so now I just have two numbers that I need to subtract. This is now just combining like terms. I'm going to do the 8/3 and the minus 1/3 to give me 7/3, just because it's easier to add those two because they're already like terms. And then I've got a positive 2 and a minus 1 because this negative applies to both items in the second set of parentheses. So 2 minus 1 is 1. So I get 7/3 plus 1. So that is 10/3, or 3 1/3. So it was somewhere between 3 and 4 like it looked from the picture, but that's the process. Antiderivative, plug in 2, plug in 1, subtract the results. And that's how we find a perfect area under the graph. So here's my next example. The function is x to the 2/3. And I've got it mapped out to where I see 18 boxes approximately, probably a little bit more than that. I've got a few that are going above the graph, but I've also got some empty space in here. So I'm thinking somewhere 18, 19, 20 range. So let's do that same process. Antiderivative, x to the 2/3. So x to the 2/3 is x to the 5/3, right? I'm adding 1. And that's over 5/3, but I'm going to, in the same step, instead of putting 5/3 on the bottom, put 3/5 out in the front. 8 and 1 are my limits of integration. So now I need to sub in 8. If I plug in an 8, I get 3/5 times 8 to the 5/3, and then I'm going to plug in 1 and get 3/5 times 1 to the 5/3. So I've chosen 8 and 1 specifically because those are numbers that I can take a cube root of. It might look like 8 to the 5/3 is a value that you can't find without a calculator, but 8 to the 5/3 is just 8 to the 1/3 and then to the 5th. So 8 to the 5/3, that's 8 to the 1/3 is 2, 2 to the 5th is 32. So this is 3/5 of 32. Okay, so make sure that 32 makes sense. We took the cube root of 8 first, and then we raised it to the 5th power. 1 to the 5/3, that's easier. 1 to anything is 1, so this is just minus 3/5. So let's see, I'm going to do 3 times 32 is 96/5, and minus 3/5 is 93/5. This is a suitable way to express your answer. And then I could also, to compare it to my guess, 95ths is 18. 5 goes into 90 18 times. And so that gives me 18 3/5, or 18.6. And there we go. So that confirms my guess based on my picture. But again, this is our perfect area. This is the exact amount of area under this graph between x equals 1 and x equals 5 using the fundamental theorem. Okay, so there's a few trig derivatives that we can take at this point. I'm going to do the integral from negative pi over 6 to positive pi over 6 of secant x tangent x. Of course, that's because this is one of the 6 trig antiderivatives I know. The antiderivative of secant x tangent x is secant x. Notice in this definite integral, there's no plus c's. When I have these limits of integration, that's a different process. I don't need to do a plus c at the end of these. I just need to do the limits of integration, top and bottom. Okay, so since the derivative of secant is secant tangent, the integral of secant tangent is secant. And so now I just need to plug in secant of pi over 6 minus secant of negative pi over 6. Okay, so secant of pi over 6, we have to go back to our unit circle. Pi over 6 is this first spot. Secant is the inverse, or the reciprocal of cosine. So the cosine here is the square root of 3 over 2. Secant would be 2 over the square root of 3. I'm not going to worry about rationalizing that right now. Then I have secant of negative pi over 6. Well, negative pi over 6 is here. And it has the same cosine, therefore it has the same secant. It's also 2 over the square root of 3. And when I subtract those two, obviously I get 0, which might seem like a mistake at first, but remember, area underneath a curve is considered negative when you're integrating. So the area I found was this combined area, and the area under the axis canceled out the area above the axis. So I could have answered this one before I ever even took the antiderivative. If you've got a symmetrical function with some area below and area above that cancels each other out, you're going to get 0 every time because this negative area canceled out this positive area. Okay, so while we talk about integrals, there are going to be some that are impossible to do by hand, and some that is just not convenient to do by hand. So we'd like to be able to evaluate these in a calculator. So Math 9, that's the key in the calculator. The FNINT for function integrate. That's the function you want to use to find these areas in your calculator. If your calculator is a little bit newer, you hit Math 9, you're going to get this. And that's a little more user-friendly. You just plug in the limits of integration, the function, and then dx, assuming you're using x as your variable. If you have a little bit older calculator, when you do FNINT, it's just going to pull up the command and this opening, the start of these parentheses. If that's if your calculator's older, you first type in the function, then you type comma x, and that's like your dx. You need to tell your calculator what the variable is. Then you type your lower limit, comma upper limit. And that's how you input an integral into an older software on a TI calculator. But the majority of you will have this new version, but in case you have an older version, this is this command is how you would evaluate this integral. Okay, so that's the solution to our problem, the fundamental theorem. It is a big one. That's why it's called the fundamental theorem.